Okay, thank you, and thanks to the organizers for setting up this nice workshop and inviting me to talk here. Uh, well, the punchline of the talk is that we are able to construct a supergravity solution, which is dual to a confining theory with non-zero baryon density, and we can do this without introducing flavor branes. Okay, so that will be the summary. So all the difficult details about the supergravity equations, the numerics, and so on, they are merit of my collaborators, Anton Faedo, who is also at Oviedo, and Javier Subils, which is at Nordita and is moving to Utrecht this fall. And it's based on these couple of papers. Now, the motivation to do this is coming from QCD. So this is the phase diagram with the temperature and the baryon chemical potential. And then there are going to be some new heavy ion experiments that are going to explore the large density regime of QCD. And also there are observations, astrophysical observations of neutron stars and coming from also from binary mergers, the gravitational waves that are produced by these mergers that are putting constraints on the properties of matter in these neutron stars. And this happens at densities around this range. And the interesting thing about this is that this range of densities is outside the reach of first principle methods in field theory. So we cannot use perturbation theory because this is a strongly coupled regime. We cannot use lattice QCD because of the same problem. We are at finite density. And we cannot use effective field theories that are fit to nuclear matter experiments that are valid like at densities close to the saturation density or below, but not above. So for these reasons, maybe gauge gravity duality can be useful to study this kind of matter and can give us some further information about the properties of strongly coupled theories at large densities. Now, there are two ways one can approach this. One is to study top-down models with an explicit string theory realization. And then this is not going to be QCD, of course. It's going to be a much more well, it could be a more symmetric theory, or it's going to have different matter content. But maybe we can use this to extract some qualitative lessons. And the other approach is to use bottom-up models. Then you just construct some supergravity action and you try to fit to lattice data wherever it's available and to experiments. And then you use this model to study the finite density region. So for this talk, I'm going to focus on top-down models. Okay, and I'm not going to try to fit any of the properties of QCD at this density. I'm just interested in finding some particular model with some, which is at a strong coupling, is confining, and have this finite baryon density. Now, the way we usually introduce flavor and baryon charts in holography is through flavor branes. So this was originated in this paper of Katz and Katz. So just you have your stack of color branes where the gauge theory lives. The usual case of n equals 4, you will have just the 3 branes. And then you add additional branes, the flavor branes, in such a way that you have also fundamental matter in the intersection of the D3 and the D7 branes, or the color and the flavor branes. Okay, so then you take the larger limit, replace the stack of color branes by the near horizon geometry. And then you are left with the flavor branes in the geometry, which are typically treated in a probe approximation, although you can also consider their back reaction. And then the degrees of freedom that live on these probe branes corresponds to the mesonic degrees of freedom in the dual field theory. Okay, so among the fields on the D7 or the flavor branes, you have some abelian gauge field, which is the dual to the U1 baryon current in the dual field theory. Now, the baryon density then corresponds to the electric flux of this gauge field inside the brane. And because the fields in the brane are in the adjoint representation of the flavor group, there are no charge fields on the brane for this U1 baryon symmetry. Okay, so in principle, one could only introduce some electric flux if you introduce sources, and then these sources can be strings ending on the brane, but typically they will pull down the brane. So essentially, if you have a black hole horizon, what will happen is that you will have the brane falling into the black hole, and then the electric flux is coming from the horizon, and all the charges are behind this black hole. So this means you will be in a deconfined phase. Okay? So this is the way you can describe more easily some baryon charge density using these flavor branes in the deconfined phase. Okay, but we are interested in describing baryon charge density in a confined phase. Okay, so we have to do something different to this. Now, people know how to describe baryons in holography. So if we think about the field theory, a baryon will be like some antisymmetric combination of the quarks, and it contains in color. So it contains like NC fields. So it's a very heavy object in the larger limit. And what happens is that in the holographic dual, that corresponds to some kind of brane. It's typically a brane that is wrapped in the internal directions. So in the standard model people use to describe the dual to a Yang-Mills theory with flavors, the Witten-Sakai-Sugimoto model. Then what happens is the color branes are different branes wrap around one circle, and then with antisymmetric boundary conditions. And then you introduce the flavor branes as D8 branes. And then the baryon branes corresponds to different branes that are wrapped on some S4 in the dual geometry to the color D4 branes. Okay, so you can see the number of baryons inside the 8 branes as the value of this integral, which is some instanton number on the D brane. Okay, so essentially the baryon in this tab corresponds to some kind of soliton inside the flavor brane. Okay, now if you want to describe a finite density phase, then you have to consider multiple instantons, so multiple solitons. And then, well, this is going to be, first of all, a non-homogeneous configuration, and second, very complicated to find, especially if you want to have a large density, so a large number of baryons. Now, you could try to go around this issue by considering something which is not exactly a solution of the equations of motion, or it's a solution, but it's singular. So you will have problems at the singularity, like maybe you need to introduce alpha prime corrections or things like this. So this is the approach that most people have used to describe dense QCD matter and apply it to these neutron stars. Okay, so this requires some additional phenomenological assumptions, and depending on the assumptions, you get different results. Okay, so there is no like an universal nice behavior for this finite density if you use these homogeneous configurations. Okay. So it seems that flavor branes have these issues. So this is what people have used. So we might want to try to do something different. So instead of considering flavor branes, let's consider whether we can have a baryon symmetry just in supergravity. Okay, and this is possible, and it's known. So I think the canonical example will be the so-called Klebanov-Strassler theory. Okay, so this is represented by a quiver. So this means that you have a UN gauge group. There is another UN plus M gauge group. And there are some fields in the bifundamental representations of this group. And this theory is confining, n equals 1 supersymmetric in 3 plus 1 dimensions. And the symmetry that is called baryon symmetry corresponds to a phase rotation of these bifundamentals with opposite phases for the two types you have. Okay, so you can construct baryonic operators with these bifundamental fields. Okay? So that's why this is called the baryon symmetry. Now, one interesting aspect of this theory is that when you flow in the RG, when you go along the RG flow towards the infrared, there is you can look at the supergravity solution, and then you see that the fluxes are changing, that are dual to these ranks of the gauge groups. And then you can interpret that as some kind of duality cascade that takes you from the original UN and n plus m theory to a single theory. So this is just n equals 1 super Yang-Mills, which we know is confining. Okay? So in the infrared, this will describe the kind of theory we really are interested in. Now, baryons in this setup correspond to objects that should be coupled to some particular components of the supergravity fields. Okay? And contrary to the usual R symmetries, the U1 baryon symmetry in this setup doesn't correspond to an isometry. It corresponds to some gauge transformation of the Ramon-Ramon forms. Okay? So this means there are no fields in supergravity that are charged under this symmetry. Only there are some type of branes that are wrap branes that are charged under this symmetry. So it seems that we go back to the same problem we had with the flavor branes, right? We need to introduce these heavy objects to have charged objects. But there is some difference, and the difference is coming from the structure of the action in the deep brane and the supergravity side. Okay? So in the case of the deep brane, the action essentially is such that the abelian part is completely decoupled. But in the supergravity setup, you have extra abelian gauge fields that are coupled to the baryonic gauge field. They are coupled through the kinetic terms, and they are coupled through topological terms. So there is some hope that if you have a solution in supergravity which is not completely trivial, you can turn on the baryon charge density even without having these branes around. Okay? So this is the thing we want to explore. We are not going to study Klebanov-Strassler because it's very complicated, but we're going to consider a simpler version of Klebanov-Strassler, okay, which lives in a lower number of dimensions. Okay? So I'm going to present this other theory now. So the theory is going to be a solution of type 2A supergravity. Okay? And in the ultraviolet, it's just dual to D2 branes. So that means it's dual to a 2+1 super Yang-Mills theory in the ultraviolet. And this is the metric corresponding to the dual geometry. So you have here the field theory part. These are the 2+1 directions of the field theory. There is the holographic radial direction. And then there is some internal space that contains some 4-sphere and some 2-cycle. Okay, so internal space is some deformation of CP3. Now, there is also a non-trivial dilaton that I'm not showing. And also you have some fluxes that tell you what are the ranks of the gauge groups in the dual field theory. So there is some 6-form flux on the full internal space that gives you the number n of colors. And then you have some flux F4 on this 4-cycle that gives you the shift in the rank between the two color groups. And then you can have an additional 2-form flux on this 2-cycle. And I will talk a bit about what this means later. Now, you see this work factor, B. So if we have that this work factor is going to 0 at some finite value of the radial coordinate, that corresponds to having a black brane. And that's dual to the deconfined phase in this theory. Now, we also have this work factor here. So if what happens is that this work factor that multiplies the 2-cycle is going to 0 in a way that the metric is regular, then we have a geometry which is ending at a finite value of the radial coordinate because this cycle is collapsing, and that should be dual to a theory with a mass gap. Now, there is some subtlety of whether this is confining or not that you can only see if you uplift to M theory, okay? And it depends on this K here. So what happens when you uplift to M theory is that the dilaton becomes the radius of an additional direction. And then it can happen that this is just an ordinary circle, like separated, like topologically separated from the rest. So you just have this topology, and this happens when K is equal to 0. Or it can happen that this circle is non-trivially fibrated with the rest of the geometry, and you actually find that the topology, when is a four sphere. So it combines this two cycle with the radial direction with the dilaton, and then this is the topology at the origin when k is non-zero. Now, this is related to the confinement and not confining, because a fundamental string, when you go to M-theory, is just an M2 brane wrap around the dilaton direction, the M-theory direction. So if you have k equals to 0, then what happens is that this circle is not going to, has a finite radius everywhere. So if you try, you cannot wrap an M2 brane here because it doesn't have anywhere to end. So that means you cannot have an isolated fundamental string. So that's confinement. But if k is non-zero, then actually this circle is going to 0 smoothly. So you can wrap an M2 brane here, no problem. And then you can have isolated fundamental strings. So it means that even though there is a mass gap, there is a cycle that this collapses into 0 size. The theory is still not confining. OK, so the dual field theory is similar to this. It's also a Quiver theory, similar to Klebanov-Strassler. So again, there is a UN times UN plus M gauge group, and there are bifundamental fields. This has n equals 1 supersymmetry in 2 plus 1 dimensions. And this means that one cannot apply any of the nice tools of supersymmetry. For instance, one cannot use localization for this theory. So it's the closest to a non-supersymmetric theory that a supersymmetric theory can be, if you want. So there are some works about n equals 1 gauge theories that have been done to study the phase diagram and things like that, but not for the particular one we are interested where this k is 0. So everything that is known is coming from this gauge gravity duality. Now, there is another similarity with Klebanov-Strassler, is that if you look at the fluxes, there is also a change in the fluxes with the radial direction that you can interpret as a duality cascade along the RG flow. And this was already something very similar was already discussed for the ABJ theory. So it's also realized in this setup, but with much less supersymmetry in this case. OK, so now about this K that is, if you're familiar with ABGM, then you will know that this K is related to a Chen-Simons for the gauge fields of this form. So these A1 and A2 correspond to the different gauge group factors. And then a possible interpretation of the property I told you about having confinement or not might be that if K is non-zero, you give a mass to the gauge fields. So you gap the system before it's able to confine. And when K is 0, then the gauge fields are gapless, but then the theory confines dynamically. Okay? That's just a possible heuristic explanation. Now, as I say, we will restrict to confining theories with K equals to 0. And the scale of the mass gap is related to the top coupling in 2 plus 1 dimensions, which is dimensionful, times this factor M over N. And then the thing is, in order for the supergravity solution to be valid up to some sizable range in the gravity dual, then we want this ratio to be small. Okay? So the limit is going to be that N goes to infinity, M goes to infinity, but the ratio is a small number, but fixed. And that allows a separation of scales. OK, so now how do we describe the baryons in this case? So first, we have to talk a bit about local operators in this kind of setup. So we're going to consider a local operator that consists on a brane, which is completely wrapped in some part of the internal space, except for one direction. So if the direction was time-like, then it would be like a particle state, no? Like the baryon vertex. But we're going to take this direction to be along the radial direction, and it can end at the boundary at one point, and that describes a local operator, a very heavy local operator that you have inserted in your dual field theory. Okay, but the volume of this brane is completely space-like. Now, in this theory, we have two types of local operators that we can introduce depending on the type of branes that we are wrapping in the internal space. So in order to, let's say, guess the dictionary, one has to look at a more supersymmetric theory like AVGM or AVJ. So there, the dictionary is that the D0 and D2 branes are dual to monopole operators. So that means around them there is some non-trivial magnetic flux. And then there is a conserved U1 current that corresponds to the Hodge dual of the magnetic fluxes, essentially. Okay, so there is a U1 magnetic conserved current, which is just a topological current in some sense. Now, the other class of local operators that you can insert are baryons or dibaryons operators, and they are dual to D4 or D6 branes that are wrapped in the internal space. And then you have the ordinary baryon current that you can construct with these bifundamental fields. Now, it turns out that whether you have monopoles or baryons depends on whether these branes will end or not on the boundary. So let me go a bit in more detail about this issue. So if you have the gauge group to be UN cross UN plus M, then there is the U1 abelian part of this that generates this U1 magnetic symmetry. No? It does the magnetic flux. The Hodge dual of the magnetic flux of the abelian part of this is the U1 magnetic current. And then it means you have these monopole operators that are dual to the D0 and D4 branes. And the would-be baryons or dibaryons are not gauge invariant because they carry a charge under this abelian part. So they are not gauge invariant, and they shouldn't be considered. If instead you have SU cross SU, then you won't have monopoles because you don't have this magnetic flux anymore, right? There is no abelian component. But now these guys are gauge invariant, so you can have baryons and dibaryon operators, so you have a U1 baryon symmetry. Now, for each of these branes, we can have an electric coupling to some Ramon-Ramon form, no? According to the number of dimensions. And is related to, through Hodge duality in the bulk, to another complementary set of the Ramon-Ramon forms. No? So you see that the D0, D2 is complementary to the D4, D6. Now, the dictionary is such that if you impose Dirichlet boundary conditions for this, for one set, you have to impose Neumann boundary conditions for the other one. And then if you want a brane to end at the boundary, then you need to have the Dirichlet boundary condition. Otherwise, the brane cannot end at the boundary. Okay? So that's how it works. So this means if we impose Dirichlet boundary conditions for the 1 and 3 forms, we can have monopoles, but not baryons. And if we impose Neumann boundary conditions for the D0 and D2, for the C1 and C3, then we can have baryons and dibaryons, but not monopoles. So this is essentially the table that summarizes which gauge theory you are looking at, depending on the boundary conditions of the Ramon-Ramon forms. So knowing this, now we are going to find the non-zero density states, but we are going to do it in a roundabout way because it was simpler first to construct the solutions for the theory with monopoles. Okay, so I'm going to construct the solutions for the theory with monopoles, and I will map it later to the theory with baryons. So what we do is, in addition to the fields I showed you before, we introduce some additional fields in the type 2 supergravity theory. And if you reduce to 4 dimensions, then what you have is that there will be a 2 form, some gauge field A1, and 2 other gauge fields A1 hat and A1 tilde and A1 hat. Okay? So these X2 and J2 are just 2 forms defined in the internal space. Now, when you find the consistent truncation, then you find in 4 dimensions, you find that this guy is the massless field. So that's dual to a conserved U1 current. And these other 2 different combinations get masses for different reasons. So there is a single conserved U1 current in the dual field theory. Now, note that this A1 is coming from the Ramon 1 form. So it corresponds to the gauge field for the D0 brane. And then this other combination of the A1 hat and A1 tilde is coming from the coupling, well, is the one that couples to the D2 branes through the Ramon-Ramon 3 form. And the way we are doing the truncation, these are our dynamical fields, so we're imposing Dirichlet boundary conditions for these guys. Okay, so it means that when we are doing this supergravity construction, we are really looking at this UN times UN plus M theory because of our choice of variables, if you want. Now, this means then that this massless field is dual to the U1 magnetic current, okay? And you can properly normalize by looking at how it couples to the branes. And what we do is we introduce some ansatz where we turn on the time component, so there will be a non-zero density of monopoles. And we introduce also a background magnetic field for the monopoles, okay? And well, we construct the solutions, and we find a phase diagram like this one, okay? So this is temperature, this is magnetic field for monopoles. And then there are two phases. One is confined, and the other is deconfined. So this corresponds to these solutions where the cycle is collapsing to zero, and these ones to black branes. And then this is done for zero chemical potential for the monopoles. And then what we find, one important aspect of this is that the charge for the monopoles in the confined phase is zero. Okay, so it vanishes. You can show it has to vanish exactly. Now, okay, apart from this, another interesting thing is that there is a line of second-order phase transitions that separates this confined phase from this deconfined phase. Okay, so I think this is the only example I know where you go from confined to deconfined through second order instead of first order. Okay, so I could talk about this. There are some other interesting things here, but let's move on to the baryon density part. Okay, so what I'm going to do is to use particle-vortex duality to construct the baryonic solutions. So if you're not familiar, I'm going to do a very brief summary. So suppose you have a theory in 2+1 dimensions, which is some kind of superfluid. So you have a Goldstone boson. And then the conserved current is written in terms of the gradient of the Goldstone. So it satisfies this equation. But you can also write this conserved current in a different way using a gauge field. Okay, so you write it in terms of the epsilon tensor contracted with the field strength. Then by the Bianchi identity, this vanishes, right? So this is another way to write a conserved current. So you can do actually a map between this Goldstone field and this gauge field. That's the particle-vortex duality. And then once you have done this map, then instead of having a scalar, you have a gauge field, dynamical gauge field. Now you see that the density here that corresponds to the number of particles is mapped to the magnetic flux of this dual gauge field. So that will be carried by vortices. No? So that's why it's called particle vortex. Okay, so we are going to do now the same thing on our theory. Okay, so now we need to impose, in order to have a baryon operators, we need to impose the Dirichlet boundary conditions for the field that couples to the D4 branes and the field that couples to the D6 branes. So that also will give some, in 4 dimensions, some gauge potentials. And then one can see that this one is the one that is massless and will be dual to the U1 baryon current. Okay, so by looking at the coupling to the D6 branes, you can find the proper normalization. Now the other one is just massive. So there is, again, just a conserved U1 baryon current. Now, to go from the description I had before to this new description with these other fields, what we can do is to change the boundary conditions. And we can do that by adding some term in the action that will do this change in boundary conditions. No? So we do the variation, then the variation of the action will correspond to the different choice of boundary conditions. Now, this is a total derivative, so doing this doesn't actually change the equations of motion. So this means we can take the solutions we had found before and then just reinterpret them with this new term. Okay, So the effect of this is actually just to modify the action. It doesn't change the solutions, it modifies the action and the interpretation. So what happens is that the free energy in the theory with baryon charge is related to the free energy in the theory with the monopoles, plus some other terms that depend on the chemical potentials and the charge densities, okay? And the chemical potentials and the charge densities are related to the magnetizations and the magnetic fields of the dual theory. Okay, so this is a simple dictionary that one can work out. Now, once this is done, then we just take the solutions, compute the free energy, and then study their properties. So this is the phase diagram now with the baryon density. So the vertical axis is the temperature, and the horizontal axis is the baryonic chemical potential. And then what we see is, again, there is this region that corresponds to a confined phase, and then there is the region outside that is dual to a deconfined phase with the black branes. Okay, and what happens, so this is computed for 0 baryonic magnetic field. And we observe that there is a non-zero baryon density in the confined phase, no? Given by the color in this figure. Okay, so we're able to find these solutions with baryon density in a confined phase. So a few more things about this is that the confined phase only exists if this magnetic field for the baryons is 0. Okay, one can think of, and this is related to the fact that the confined phase was existing only when the charge of monopoles was 0. No? There is a duality relating the two things. And one can think of this as this confined phase to be some kind of baryonic superfluid. Okay, this means that if it's a superfluid and you make the gauge field dynamical, then it's like a superconductor, and then you cannot introduce a magnetic field inside the superconductor, right? You will destroy the superconducting phase. So the fact that this is 0, one can think about it as a Meissner effect, okay? And that explains, that will explain this result. Now, in the deconfined phase, it looks like some kind of baryon ferromagnet in the sense that there is a non-trivial magnetization, and it's coming from a term in the free energy that looks like this. So there is so this was predicted in previous works that study theories in 2+1 dimensions with parity breaking. Okay, and it consists of this a term proportional to the magnetic field, and then the magnetization. You can see that is proportional to the baryonic chemical potential times a factor. So this, if you put it here, it looks like an incomplete Chern-Simons term with some filling fraction coefficient nu bar. So we study how this behaves with the temperature, and we find something interesting, that it goes to some integer value at high temperatures, like 3 times m times n. So we don't understand precisely why this happens, but it seems like an interesting feature of this theory. Okay, so this is the results. Let me just go to the summary. So, okay, this is what I said at the beginning. We are able to find the solution. And then what we would like to do is, I argue that this will be a baryonic superfluid phase because of this Meissner effect. But if it's a baryonic superfluid, there should be some kind of Goldstone bosons associated to the spontaneous symmetry breaking. Okay, so we would like to study this and find the Goldstone boson. One can extend this to other gauge theories where k is different than 0. These theories with a mass gap, but they were not confining. So this could be interesting just for the sake of exploring the phase diagram of these theories, which is not very well understood. And in this case, maybe one can compare to some field theory results that people has derived. And then finally, for the application to QCD, one would like to go to 3+1 dimensions, right? This was in 2+1 dimensions. So study something like Klebanov-Strassler. Okay, this is a much more complicated problem, technically. There are some solutions with baryon density, but only in the deconfined phase. But for the confined phase, nothing has been done in this direction so far. Okay, so with this, I finished. Thank you.
one do you think?
I don't know. Are you sure? Are you sure?
About, okay, yeah. Just as a, there are very big differences between baryons and never mind ADS-15 large N and the real world, like at finite chemical potential particularly, because at large N, baryons are typically strongly bound and they're a crystal. In the real world, they're a liquid. There is chiral symmetry. At large N chiral symmetry, the energy gap disappears. In the real world, chiral symmetry and confinement interplay in a very subtle way, and there might even be new phases, et cetera, et cetera. And, you know, I mean, in flavor blanes, large N, these large N effects pretty much automatically are guaranteed, which make it different from the real world. Do you think this can be used to mitigate these issues?
Well, at least this allows you to find some homogeneous finite density state in the confining phase, which is more than what we were able to do before. Right. So whether this is going to, match with QCD, I cannot tell. But the hope is that maybe there are some properties that are general for these kind of solutions that could apply to QCD, like it happened at high temperature. At least if the phase at least looks similar. No? It looks like a baryon superfluid, so that's more similar to what happens in QCD. So I don't know if...
Sorry, by homogeneous...
No.
By homogeneous, you also mean that the two baryon correlator sort of is flat, or because homogeneous can mean homogeneous on average but rapidly oscillating, like a liquid.
No, I mean just that the density is constant everywhere.
Okay.
And there is nothing that depends on the spatial coordinates.
Yeah, it doesn't fluctuate. It's really constant.
Yeah,
okay.
Nothing.
Thanks.
No.
Hi. Thanks for the talk. I have a question, and then perhaps some aside comments, which I can't resist making here. So the question is, before turning on baryonic density and so on, for the solution, let's say the analog of the Klebanov-Strasser solution, do you understand that in terms of the cascade of in detail with the quiver and with the cascade of an n=1 field theory in 3 dimensions and so on?
The question is if I understand how the cascade works. So.
At the beginning, you explained that there is a quiver similar to the Klebanov-Strasser.
Yes, so in Klebanov-Strasser is a set of cyber dualities. So, so what happens is one of the gauge groups is becoming strongly coupled and the other weakly coupled.
Yeah, I know and that. But do you understand the 3-dimensional version?
It's similar.
It's similar.
It's a similar kind of duality, but in 3 dimensions.
Okay, and okay.
It's like the two gauge couplings are running in a different way. And then when one becomes strongly coupled, then you can do the duality.
Okay, and then if I can make a comment, some years ago I had a solution. I discussed the solution which was with a student of Carlos, and was essentially a similar version for 3-dimensional theories to another solution which I constructed with Juan. Which was discussing the relation between the Klebanov-Strasser solution and the solution of Carlos and Juan. So the solution that I constructed with the student was, similarly, there was a relation between this cascading type of thing and the solution of Horacio with Juan. So all the characters are here. I'm wondering if there is I mean, at the time we didn't understand the field theory discussion of this relation. So it looks like there is I mean, here in the infrared you are supposed to get pure n=1 Young Mills, which is the same as in the solution of Horacio and Juan. So I think there could be something to understand better in that case. But that's in this fully supersymmetric case before turning on the baryonic density and so on.
Yeah, that might be. I don't know what is the equivalent to the Maldacena here, but
sorry,
I'm not sure what are the equivalents of all those solutions in the 2+1 case. But,
we can discuss it later, but in the four-dimensional case, the connection is through this so-called baryonic branch of the Clabanon-Strasser solution. There is one parameter deformation that takes you basically to the solution of Carlos and Juan.
Yeah.
And similarly, in the solution here, there is one parameter deformation that takes you from this Pope et al. Solution to the solution of Horacio and Juan.
Okay.
And
that will be interesting.
Yeah,
maybe that.
Yeah.
We'll discuss that.
Okay.
Yeah.
Thanks.
Yeah.
Thanks. So your supergravity solution with CP3, which is a twistor space of S4, can you do you can presumably have such solutions with other twistor spaces. Are the field theories for those known, and is there a similar story? So you can replace it by CP2, for example. What's the field theory in that case?
So you want to replace the deformed CP3 by a different geometry?
Yeah.
I think you can generalize to, well, this type of geometries, but the expert is Anton. So
Sorry?
The expert is Anton Feider on this, but in principle, you can change the CP3 by something which is a nearly color geometry.
Yeah, exactly. That's exactly what I'm saying. Yeah. So your d omega squared 4 is the 4 sphere in this case, right?
Yeah. Here, yes, this has a 4 cycle and a 2 cycle. Maybe you can have different topologies. Or I don't know.
I think you definitely can. So I was just asking if there are field theories for those or not. No.
I don't know. We don't even know exactly what the field theory dual to this is. We know the supersymmetry and probably what is the gauge group and things like that, but not completely what the dual field theory is.
Okay.
So because of it has very little supersymmetry.
Okay.
So just quickly about this second order phase transition. I mean, is that tied to the fact that you're in 2+1 dimension? Is it going to be different if you manage to do it in 3+1?
I don't know if you can have it in 3+1. Yeah. Here, the idea is, what is happening here is that, okay, let's go. When you move along this direction, you have a black hole that is becoming kind of extremal here, but in a way that it loses the horizon, so it becomes, I mean, we cannot go all the way to this line numerically, but it is, the horizon is becoming smaller and smaller. If you look at the entropy, it's going to 0. And then, yeah, so that's what allows, I guess, this to connect continuously here.
If you think of getting the QCD phase diagram, if you manage to do it in 3+1 dimensions, I mean, you don't want this feature.
Well, but this is not, this is for the theory with monopoles, so it's not related to QCD or baryon density or anything like that. Yeah.
Sorry, maybe there was some misunderstanding. In my first question, I asked if you understood the field theory, and you said you understand it in detail in terms of cascading, et cetera, et cetera. But then later, you said that you didn't understand the field theory in detail. So what was the confusion?
You were asking about Klebanov-Strassler, I thought.
No. I was asking about the 3D field theory, and you said that it works exactly in the same way as the Klebanov-Strassler,
yeah,
and I was surprised because I wasn't aware of that. But
no, I was referring, this has been studied for the ABJ. That's where you understand it. And then here, the supergravity is similar. The fluxes behave in a similar way as in the dual.
But the field theory, is there an understanding of the field theory or there isn't? In three-dimensional field theory.
In the ABJ theory, there is an understanding.
In terms of the cascade?
Of the cascade and so on, yes.
Okay, and who has done that?
Let's see if I have the reference before. Yeah, I guess Aharoni and company, but let me see if I put the reference. Yeah. I guess I have it here. So, yeah, these papers here.
Okay, and so later when James asked about the field theory understanding, why did you say that it's not clear what's the field theory?
Well, so the theory we are looking at has only n equals 1 supersymmetry. Okay, so we don't know what is the Lagrangian of that theory, for instance.
Okay, so, so this understanding does not apply to your solution. It's an understanding of something else. Of the
Yeah, let's say
ABJ
this
theory,
understanding
which is not n equal 1.
Yeah, so this is what happens in ABJ.
Yeah,
And
but it's not relevant for this solution here because this is n equal 1.
It is relevant in the sense that if you look at the supergravity dual and look at how the fluxes behave, in this supergravity dual, they behave exactly in the same way. So you cannot prove that. Right.
Right, but there isn't an understanding of the n equal 1 field theory in terms of dualities, right? Okay.
No, I mean, you don't have an understanding in field theory of how this duality works in n equals 1.
Okay, okay.
But
It's
in the
clearer now
supergravity dual,
what's understood and what's not understood.
Yeah.
Thanks.
Okay, sorry if it was not clear. No.
So regarding the last comment, I didn't understand if at the end of the day that's a superfluid or a superconductor. Because you mentioned a Meissner effect, but then you say it's a superfluid Goldstone. If there is Meissner effect, there's no Goldstone because it's a superconductor, so the Goldstone is kept out. So
Yeah, it's a superfluid, no? But I was trying to explain why you cannot have a background magnetic field. Okay, but this is easy to understand if you think about a superconductor. No? So if you have the background magnetic field, that will destroy the superfluid phase. Yeah. But you can also understand that if you make this gauge field dynamical, what will happen is you will expel the magnetic field.
But that's a superconductor then. It's not a superfluid.
Yeah,
the superfluid does not expel magnetic field.
Yeah, you just destroy the phase if you introduce the background magnetic field.
Okay.
That's what will happen in the superfluid.
So I'm confused. I mean, your gauge field is massless.
The gauge field, which gauge field?
The baryon, U1 baryon, or
the baryon is a background gauge field.
Okay.
Okay, and then what you find is that.
But when you make it dynamical?
So you could make it dynamical in the usual semi-holographic way, right? Like.
But then to have Meissner effect, that guy should become massive, like X mechanism.
So it will become massive, yeah.
It will become massive.
Yeah. I guess we have to find the Goldstone to prove that.
But there's no Goldstone. I mean, it's eaten by this guy.
So we think there should be a Goldstone, but we haven't looked for it yet.
Okay. Okay, well, we can discuss later. Sorry.
No.
More questions?
Last one, sorry, Carlos. Much in the direction of what Dario and James asked. What's the far UV of this theory? Is it ADS, the geometry? Is it ADS4?
No, it's a D2 brane geometry.
Okay.
So it's a weakly coupled gauge theory with this gauge group.
I see.
So the difference with Klebanov-Strassler is that the cascade has a finite number of steps.
Good.
So it stops
that
here.
That answers many other questions. Thanks very much.
No.
Okay, so let's thank Carlos for a nice talk. So, 2:45. Okay.